So the next speaker is Peng Chen, who's been two-step university and the dedicated application for inference behind the manifestation in those equations. Thank you.
Thank you. Thank you very much. Hi, good morning, everyone. I apologize. I registered as an in-person attendance, but I cannot travel because my kids draw some nice pictures on my passport, so I cannot travel. Well, today I'm going to talk about the projected variational inference for Bayesian inverse problems, especially in high dimensions in function space. This is joint work with Thomas O'Leary Rossberry, Omar Gadas from UT Austin, and Kui Wu from Meta, Joshua Chen from STR. And also some of the other work is joined with Ife Wang and Mert Pilasi from Stanford and Wu Chen Li from South Carolina. Let me start with one example. So here you can see the Antarctica ice sheet flow. And according to some of the estimates, it says like if all of the ice get melted from the Antarctica, then there is a sea level rise, significant sea level rise that can possibly wipe out like 40% of all the coastal city. And here we have the satellite data, satellite observation of the surface ice flow velocity. So based on this data and also the model, the ice flows following certain rules, like here, we can model it by nonlinear viscous incompressible fluid flow. It's essentially a nonlinear Stokes equations. And then the unknown parameter here is a Bessel sliding field in the boundary conditions. Essentially, it's between the ice and the land, and there is a boundary condition. And this boundary condition depends on the landscape of the ice and the land. So it is in general not known. We need to infer this parameter. So on the right, there is a piece of early work on solving their inverse problem by this is actually a deterministic inverse problem. You find the maximum posterior point, and here on the right you can see essentially a posterior a maximum posterior point for the sliding boundary condition exponential of beta. The second example is the inference of COVID-19. So here is a map of a US of different states. And there is a percentage number in each of the state, which stands for the percentage of deaths linked to nursing homes. It's essentially the number of people who died from nursing homes is a percentage. In fact, the total population of the nursing home residents are about 0.7% in US. But however, in average at a certain time, it accounted for about 40% of deaths. And there is a strong heterogeneity between the deaths from outside the nursing homes and also inside, right? Without accounting for this heterogeneity, the estimate of the dynamics of the pandemic could be quite off the track. So now I would like to know, the parameters that I can explain the data. And the data at that time we collected, actually, there are a number of confirmed cases in Texas, and this is an accumulated number of confirmed cases. And this is the daily number of confirmed cases. There is a certain oscillatory because of the lack of the report or the misreport or the delay of the report. So we can do certain like a moving average of this number. And then we also collected data from the hospitalized cases. Here you can see there is significant growth of the number of hospitalized cases in mid-April in Texas. Well, earlier than that is probably like because of the lack of a report or misreport. And there is also a number of deceased cases, accumulated number, and also a daily number. You can see it's very oscillatory. And also, in particular, we have the number of deceased cases from long-term care facilities, including nursing homes, because they have similar patterns. And there is a daily number. So first of all, there's apparently a lot of observation noise or measurement noise, right? And secondly, there are multiple data we want to fit. So the model at that time we came up with is a classical mechanical epidemiological model, which is the SEIR model. with additional hospitalized cases and deceased cases, depending on the data we have. And but here, especially we have a sort of like the two big segment. One segment is for the dynamics inside the long-term care facilities, and the other side is outside their long-term care facilities. And there is a contact matrix. The contact matrix stands for the infection between the inside and outside, possibly because of their visiting of the residents to hospitals, and there you have some infections, or the family visitors to their nursing homes in early time, or the nurse who are working in the long-term care facilities. So as you can see here, there's a lot of parameters, and so all these different parameters, some of them, they're time dependent, some of them you can take them as steady parameters, sort of like constant parameters. So this is a system of ordinary differential equations that can describe the dynamics. And as I briefly mentioned, some of the parameters are time dependent. For instance, here in the contact matrix, there is this is a contact matrix, but we can pre-multiply by a factor. And this factor explains the sort of like the transmission reduction. And as you can imagine, if there is a strong mitigation policy like the total lockdown, then this alpha would equal to 1. So essentially, there is no contact anymore. And if there is no mitigation at all, so this alpha equals to 0. And as the dynamics goes from time to time, and as the policy was implemented, so this alpha becomes also different. It becomes essentially a time-dependent parameter. And over a certain time period, it is a continuous variable, it's a continuous function. And after discretization, could become quite high dimensional, depending on the number of days you describe this data and process. There are quite a few other parameters also time dependent, and so essentially we need to infer all these parameters, both the time dependent parameters and also time independent parameters, according to this model and the data. So the way that we describe or we learn these parameters are in the Bayesian framework. So simply speaking here, as also Elizabeth introduced, in the Bayesian framework, we have the data y, and also we have a parameter that we denote as this is theta. It is in dimension d. D could be infinite dimensional, and we have a from parameter to observable map, which is a map O. And this map could depend on their underlying dynamics, like the ODE or the partial differential equations. And then we have the observation noise, psi, which follows a certain Gaussian distribution with covariance gamma. This is a relatively straightforward assumption. And then Bayesian rule says that the posterior distribution of this theta is given by the likelihood function times the prior, under the condition that this y and theta, they're independent, or the noise and the theta, they're independent. This is divided by a normalization constant, a model evidence term, which is integral of the likelihood function with respect to the prior. And in the central tasks of Bayesian inference, typically, you want to draw samples from this posterior distribution, or you want to compute some statistics. Like here, we have a quantity of interest Q. We want to compute the integral of this Q with respect to the posterior distribution. And essentially, we still need to draw samples from this posterior distribution. Well, as you can see from the two examples, there are a lot of different computational challenges for these problems. So first of all, the posterior, let's say here on the left, you can see the Rosenblatt function, or the two double banana functions. You can see it is non-Gaussian, and it's multimodal, and also it's concentrating in a local region, especially in very high dimensions. And this likelihood function typically is concentrating in a very local region. And secondly, the parameter could live in very high dimensional space, right? Like in the ice sheet model, you have the discretization of the mesh, and each of the mesh point becomes a random variable. There is a certain correlation between these random variables. And also in the COVID-19 example, you have the time-dependent parameter where after discretization, each of the, let's say, time instance or each of the day, there is a random parameter. There is a certain correlation of these parameters. And typically in high dimensions, there is this notion of a curse of dimensionality. Essentially, the complexity grows exponentially for many of the methods. And lastly, there's this map could become expensive to evaluate, especially if it involves large scale partial differential equations. You might have to solve it using supercomputers, right? So there, over the years, the last decade or two, and there are significant many different kinds of methods that have been developed to address these computational challenges. So the first category is about like the accelerated MC-MC to increase the number of effective samples using, let's say, some of the geometry information like the Langevin or Hamiltonian MC-MC, using local geometric information like the gradient and the Hessian information. And there is a dimension reduced MC-MC in the high dimensional problems. Essentially, you want to exploit the intrinsic low dimensionality of these problems by projecting down the high dimensional parameter to the intrinsic low dimensional subspace. And then there's this randomized optimized MC-MC. So turning this sampling problem to optimization problem, but still you draw the random samples for the data, and also you solve the sort of like optimization problem to get the map point according to each of the random sample for the data. And then there is a second class of a method, which is a direct posterior construction and a statistical computation. For instance, first is a Laplace approximation. You want to approximate the posterior distribution by simply a Gaussian distribution at the map point. And then there is a deterministic quadrature, especially the sparse Smolyak quadrature or high order quasi-Monte Carlo deterministic quadrature. And then the third class is a transport methods, transport map-based methods. You want a transport or you want to push a certain reference measure from, let's say, standard normal Gaussian distribution to the target distribution to the posterior distribution. And these transport maps can be constructed by either polynomials or radial basis functions, like in the kernels, or deeper neural networks, or other type of representation for these transport maps. And then the last class I want to mention is about the surrogate model to reduce larger scale computation. So essentially, it can approximate from the parameter to the observable map by polynomial approximation, or you can use the model reduction techniques that it can quickly evaluate from the parameter to observable map using either proper orthogonal decomposition, reduced basis method, and other most recently developed like deep neural networks, neural operators, let's say. And there is multi-level, multi-fidelity sampling, either MC-MC sampling, stochastic collocation sampling, and also multi-fidelity, multi-level variational inference sampling. So our target is to develop a fast and scalable inference method in high dimensions. The high dimensions are both in parameter dimension and also in state space. State space and simply means, for instance, here in our partial differential equations, we have a state variable living in high dimensional space. So we want to address them using projected transport map in parameter space, and also reduced basis approximation state space. But in this talk, I'm going to focus on the first class of method. You can take a look at this paper for the reduced basis approximation combined with Stein variational inference. All right, so for the transport-based method, I have here the notion of optimal transport. So essentially, you want to move, let's say, a pile of dirt from one location to another location with a minimal cost. And here is T is a transport. So essentially, you want to solve some optimization problem in order to move this mass to another place with a minimum cost. And this is a general formulation, but mathematically speaking, in our context, the transport-based variational inference takes a certain formulation. So essentially here we assume we have a optimal transport T star, the maps from the parameter dimension RD to the RD. And this optimal transport map, is obtained by a minimization problem. So it's the minimization of this transport map in the transport map class of calligraphic T. And the criteria is, certain notion of the difference between the push forward map T of T sharp of our reference measure or prior density, let's say, to the posterior distribution. And here we measured it by parallel divergence. The Kullback Leibler divergence is defined as the log of pi1 over pi2 integrated with respect to pi1. So essentially here, as you can imagine, you want to draw some samples from the prior distribution, and you want to push by this transport map forward to the posterior distribution. And when the posterior distribution gets to be quite complicated, and then the transport map could also become rather complex, nonlinear, or it's rather challenging to compute this transport map directly. So here we adopted this, sort of like a composition of transport maps from T0 to TL. We want to move the particles or the samples step by step from the initial bunch of samples to the samples that follows posterior distribution. So each of the transport map T0 could be relatively simple. So for instance, here, if we solve the optimization problem by, let's say, gradient-based method or some other type of method, each of the step of the optimization, we can tag it as a transport map that transport the particles from where it is plus some perturbation map. So you want to move from the original location to a perturbed location, which is represented by this phi of L. L stands for the step. And this R of L stands for a sort of like a step size or learning rate. And this is theta L at the step L, and N stands for the nth particle. So you have like a bunch of particles. Apparently this phi of the head is a sort of like estimate of this transport map or perturbation map. It can be obtained by a certain optimization method within a certain function class for the transport map. For instance, we can apply gradient descent method or a Newton method, quasi-Newton method. In fact, here you can see on the right, there is a cartoonish representation of the particle pushed forward to the posterior distribution by a Stein variational Newton method developed a few years ago. Mathematically speaking, here's each of the step you have a density pi 0 to pi L plus 1, and this is pushed forward by the composition of the transport map from T0 to TL, and each of the pi L plus 1 is given by the push forward of the TL for the pi L. So now, suppose we're at the step L, we want to like sort of find a transport map TL by minimizing this functional. So right now we are at a pi L. We want to find a perturbation map, which is I plus this Q. Q is a perturbation map, right? And this got pushed for the pi L closer to the posterior distribution pi Y. And we want to find this Q by solving the optimization problem. So essentially, this is a cost function or energy function with respect to our perturbation map Q. And then after this one-step optimization, we can get this TL given by this identity plus this perturbation. And R of L can be obtained by either you prescribe some like a learning rate with dynamic change, or you can find this R of L by certain globalization method, for instance, like a line search. And then in the gradient descent method, there is a so-called steepest descent. So essentially, this QL is given by the gradient of this cost function with respect to Q, evaluated at Q equals to 0. And this was developed as a Stein variational gradient descent method based on the approximation of this QL using reproducing kernel Hilbert space. And then the second method is a Newton method. You want to solve the linear system by, for instance, here you have the Hessian of the cost functional. On the right, you have the gradient of the cost functional. And you want to test it with respect to all possible test function in the function class. All right, so here, this is a little bit more details about the specific or explicit form of this gradient and Hessian. And so essentially, you can take the first variation of this cost function with respect to Q. Q now is a function, right? And you can test in the direction of V. V is also in function from the function class. And now this is explicitly given by the expectation with respect to the current density pi L. And here you have the gradient of the log of the posterior distribution, a posterior density. And you have pre-multiplied by this matrix well, it's not a matrix, but it's a vector functions on V of theta in dimension D, because theta now is in dimension D. And you also have a term of the trace of the sort of like the Jacobian of this function with respect to the parameter theta. And the second order term, you can also take the second variation, and it becomes a bit more involved, but essentially it involves the Hessian of the log of the posterior distribution. And then here's the Bayesian role again. So as a posterior distribution, you have the likelihood prior. The question is we need to take the log of the posterior and also the gradient and the Hessian. So once you take the gradient, for instance, here, and you actually get rid of the normalization constant or the model evidence here, because model evidence is typically is high dimensional integral, is intractable to compute it. But right now you can get rid of it with this gradient computation, and it can only you can evaluate sort of like the prior density and the likelihood function, and that's it. So the next problem is that what kind of like a function space for your transport map, right? So here, for instance, we have dimension D. D could be infinite dimensional, let's say, and it's a tensor product function space. For each of the dimension, we have a function space of H, and it's a tensor product of all this different function space. And this function spaces can be represented or approximated by, let's say, tensor product of sparse polynomials. It can be approximated by radial basis or kernel functions, or also neural networks. And in particular here today, we're going to focus on the radial basis function for the Stein variational gradient method and Stein variational Newton method, and also the Wasserstein gradient method. And I'll briefly mention about our neural network approximation of the Wasserstein gradient a bit later on towards the end of the talk. So here, specifically, we pick the reproducing kernel Hilbert space H. So essentially, for such a space, there exists a function or a kernel here, K, of theta for every parameter theta in parameter space. And it satisfies the property, the reproducing property. Any of the function V evaluated parameter theta can be given by an inner product of this V and K of theta. Now, this is a Hilbert space equipped with the inner product here. And now it implies that the existence of this K theta prime for every theta prime. So you have the evaluation of the kernel at theta, and you have the inner product here, and then this inner product gives you a sort of like a reproducing kernel, K of theta prime. There are different choices of this kernel. For instance, could it be like a bilinear? It could be polynomials. It could also be radial basis functions, and radial basis functions are quite common in this reproducing kernel choice. And also there are many different types of radial basis functions. So here's one particular type. This is sort of like the square exponential square. So essentially have this parameter minus this parameter theta prime. You have an exponential of this square with certain metric, and typically you can pick this metric as a identity, right? And that is a simplistic case with a certain bandwidth of H here. And but in particular here for high dimensional problem, there is a this geometry of the posterior that it can take advantage of. So in this paper of a Stein variational Newton, they propose to take the average of the Hessian of the log of the posterior, evaluated at the current density pi L. So essentially you can use sample average approximation of this Hessian term. But however, typically this might be quite expensive to compute. And then to account for the dimension here, H is taken as a dimension here. So now for this reproducing kernel Hilbert space H, we have a sort of like a finite dimensional approximation, which is given by the kernel evaluated at given particles theta of n of L at the current particles, let's say. And we have the kernel function. We get a span of all this kernel function. Now this becomes our finite dimensional approximation of this space. And then, so in this function space, this theta and L are the particles transported from originally their prior samples, right? And step by step by these transport maps. And so that's pretty much about how we define this reproducible Hilbert space and also the perfect kernel that we can tag. And then with this reproducible kernel property, and there is a for the gradient descent method, you can actually evaluate this gradient test with respect to a certain function v, and the inner product is taken in the function space of h of d is actually given by this term. So by the reproducible kernel property, you can sort of like using this kernel here. And now the first term only involves the expectation with respect to the current and density of this gradient times this kernel, and also there is the gradient of the kernel function itself. So by this reproducible kernel property, for this gradient descent method, we have the perturbation map Q of L evaluated a given particle here is given by this gradient of J of L for Q evaluated at 0, and then you have the theta of NL. Now you have explicit form coming from here of this update or the perturbation map. And so essentially here you have an expectation with respect to the current density. So you can use sample average approximation with the current particles, right? You have the average of all these particles, and you can plug it in here. And so every time step, you only need to compute this gradient of the log of the posterior and weighted by this kernel, and also with additional term of the gradient of the kernel. So practically speaking, this first term is sort of like draw all the particles close to the posterior distribution from where they are, right? Like you get the gradient of the log of the posterior. And so there is a weighted term. So essentially they talk with each other. All these particles, they sort of like talk with each other, and they go together towards the posterior distribution. And the second term here is a gradient of the kernel itself. It plays a role of pushing each of the particle away from each other. So essentially, the so-called repulsion force term. And in this case, all these particles, they sort of like they sense each other. They will not collapse to the single point if this gradient of the kernel plays an effective role. However, in high dimensions, typically, this is a problem. In high dimensions, the kernel tends to be the sort of like a delta function, and they would lose the effect of repulsing each other, and then eventually they will collapse sort of like to the local modes to the map point. So now this is the basic algorithm. You're going to push the samples step by step by this perturbation map. As I said, in high dimensions, there is this problem of the cursor dimensionality. So essentially, you can see here by simply applying this SVGD with growing dimensions, dimension goes from this is log 2 scale, and so you have the mean square error of the variance. Essentially, measure the variance of the particles that converged towards the posterior. So for a certain test problem, here I can see that the variance represented by the SVGD samples, they become less and less accurate. And but if with projected standard variation of gradient descent, you can sort of like preserve the variance in high dimensions. And the intuition comes from the posterior and the prior. They're only significantly different in a intrinsically low dimensional subspace. For instance, here is a plot. We have the prior as a blue line and the posterior as a red line here, the marginal prior and posterior. As you can see here, in the first dimension, after you properly arrange them, the posterior is quite concentrated. And here's a dot of the map point. And it's quite different from the prior, right? As you can go to higher and higher dimensions, the marginal posterior and the prior, they become closer and closer. And also you can see from the marginal joint density. So now the problem becomes, how do you find such a subspace? And then you can sort of like project a parameter into this subspace. This subspace informed by the data. So you only care about this subspace for the update of these particles from the prior to the posterior distribution. So here is a the sort of like the way that you can find the subspace by simply solving this generalized eigenvalue problem. And what is this generalized eigenvalue problem, right? So on the left-hand side, you have the H. Sorry for the bad notation. The H is sort of like the Hessian matrix or a gradient information matrix. It's different from the reproducing kernel Hilbert space. So essentially here, it involves the information from the data. And on the right-hand side, you have a covariance C. Suppose that parameter C follows a certain Gaussian distribution as a prior distribution. So you can solve this generalized eigenvalue problem. And here on the left-hand side, it is measured by, this sort of like a gradient information matrix. You have the gradient of the potential. Potential is given by the log of the likelihood function. And you have this sort of like this matrix. And then you can solve the generalized eigenvalue problem. You have the eigenvalues that measures sort of like the relative sensitivity of the data and the prior information. Suppose that this eigenvalue is pretty big. That basically means the data plays an important role in that corresponding dimension or corresponding direction of the eigenvector. And if the eigenvalue becomes much smaller, and that basically means that the data does not tell you much information from that direction represented by the eigenvector. So here's the example represented by this COVID-19. So after discretization of the time-dependent parameters, we get about 1,500 parameters, and we can solve this generalized eigenvalue problem. Step by step, this L stands for the step. As we can see here, so the eigenvalue decay in the log 10 term very fast, many orders of magnitude, right? So here for the first like 50 at the initial step, you would have a decay of 7 orders magnitude of the eigenvalues. So essentially, out of this 1,500 dimensions, you only have a certain number of dimensions that are important. And as you go step by step, all these parameters, all these particles, they're sort of like they're all moving towards a certain local region. Then the dimension, the intrinsic dimension also becomes smaller and smaller. So now, given this vectors that are obtained from this generalized eigenvalue problem, here you can, for instance, you can truncate it up to a dimension R, and you have this eigen vectors are formed by this eigenvector phi of psi 1 up to R, and then you can actually project the parameter down to this low-dimensional subspace, and then say here this is a projected coefficient W. Now, so essentially the uncertainty or the uncertainty of the parameter that differ from the prior and posterior distribution, this sort of like uncertainty is characterized by this coefficient, this W, right? So here we have the projected posterior, and originally we have the theta, now we have the theta R, and we have a sort of like a profile function. This profile function, this is a BS rho, right? This is a model evidence. This is the original prior distribution, prior density. And the profile function is related to the likelihood function. In fact, it was shown in this paper that the optimal profile function is given by the expectation of the likelihood function with respect to the marginal distribution. And for such kind of optimal sort of like a profile function, you have the difference measured by the chiral divergence between the original posterior distribution and the projected posterior distribution. It can be upper bounded by the trailing of the eigenvalues from this R plus 1 to infinity terms, or the D terms. Imagine here this lambda becomes much smaller after R terms, and this error becomes much smaller. So here is our simple idea. It's essentially decompose the parameter into the low-dimensional subspace of theta R, and also the complement subspace. And now you have the decomposition of the prior to, and you have the profile function here. Now, since the representation of the uncertainty of the theta R can be completely given by this W, now we can essentially define our Bayesian inverse problem in the low-dimensional subspace in the coefficient space. And so here's our posterior distribution, posterior density of the coefficient. Now it becomes a much smaller dimensional problem to solve. So here we can apply the same transport map solve a minimization problem, but now it's different prior and posterior distribution for the coefficient. We can also effectively compute the gradient of the log of the posterior by a projection of this original gradient into this, the eigen subspace. And here's a sort of like the basic algorithm. You have the SVGD. You have many input. What this stands for the dimension here. Perhaps this is a dimension is quite high dimensional, and all these dimensions talk with each other as you move all these particles. And now by projection, you actually project it down to a very small dimensional problem, and you apply this SVGD with proper, let's say, curvature of the kernel function, and you can involve this SVGD in this subspace, and it becomes much more efficient, and it can alleviate their cursive dimensionality. And then after certain convergence, you can prolongate it to the original dimension, and you can project the dimension again down to another subspace that you construct adaptively. And this way, you can push all the particles step by step towards the posterior distribution. So we also implemented a parallel version of this Stein variational gradient descent. Essentially, imagine you have many particles, right? And you can allocate all these particles equivalently or equally to in a different course of your computing facilities, and then you can perform the switch or the communication of all this sort of like information in the coefficient space. And so essentially, this parallel projected version becomes much more efficient in the communication. Here's an example of you have the parameter as the Brownian motion. The prior distributions is a Brownian motion, and you have the sort of like conditional diffusion problem. U stands for the state variable, time-dependent problem. And here you can see on the left-hand side, you have the SVGD samples, like you can sample from this prior distribution. And on the right, you have the solution or the state variable U of t. You have some observations, the noisy data here, the black dots, and you have the true the process. And now if you solve the inference problem by either the SVGD and the PSVGD, you can see here the posterior mean converge to the true sort of like sample or synthetic sample, and with a pretty good credible interval for their samples. And but however, for the SVGD, it fails to converge in relatively high dimensions. And can see a similar behavior for the solution too. So here's a test of scalability. So essentially, what if you enlarge the dimensions, right? But however, fortunately, the eigenvalue decay does not change much as you enlarge the parameter dimension from, let's say, 300 to 16,000. You can see the decay of the eigenvalues are pretty much the same as with respect to different parameter dimensions. And also, this is with respect to different number of particles. If you use many more particles, decay of the eigenvalues also stay pretty similar to each other. That essentially means the intrinsic dimension doesn't change much. This is where the scalability comes from. So essentially, you can see this is a decay of the step norm. Step norm simply means like every time you move the particles from one step to another, and the distance between their move, as you can see here, it decays quite quickly, and also it decays similarly for different parameter dimensions, also for different number of samples. So essentially here, we can claim their scalability with respect to the parameter dimensions and also their samples. And here's a test of their scalability with respect to their parallel implementation. This is our time. This is with increasing number of processor cores, it decays close to the linear decay of the computing time. And here's their application of our Stein variational method. So this is the time-dependent parameter of the transmission reduction factor, this alpha t, and here we learned this parameter inside and outside long-term care facilities. As you can see, at a certain time, there is a significant increase of this transmission factor, and we also have a quantified uncertainty here. So we have all learned all these other time-independent parameters too. There is a certain uncertainty range for them, and here's a the data that we sort of like, we solved the deterministic inference problem. We can see there black dots and also the data, they line up with each other quite well. But however, with our Bayesian inference, we can also sort of like, coverage the data. Here is a quite oscillatory data with our credible interval. And more than that, so if you do some forecasting or prediction for the future, and for instance, here in the hospitalized case, if you use a deterministic inference, and this is the deterministic prediction, it is going away from the data. And the posterior mean also goes away from the data. But however, we have our credible interval. Going to the future, the uncertainty becomes larger, though this credible interval can still cover the data quite well. As you can see here, the number of deaths also cover quite well of their data. So this is the power of the Bayesian inference. And here, for the rest of maybe about 15 minutes, I'm going to talk about Wasserstein gradient flow or Wasserstein gradient descent, and also the projected version of it. So originally we talked about the optimization problem of transport map, right? Now we talk about the optimization of the density. Pi is the density in our density class or the probability density space. So it is a measurable space, and the probability density should be n equal to 1, and also is positive. So essentially, we want to solve this optimization problem in this probability density space. So we can apply also gradient method. Now here we have a gradient flow. So essentially, we take the variation of this energy functional of this scalar divergence with respect to our let's say current density pi of t, and then this is our gradient flow, right? This is our gradient of pi t equals to our minus of the gradient of this term. But however, we equipped it with a certain metric, and this is in the information metric in probability space. This is a particular information metric. This is called Wasserstein metric. It takes the form of the divergence of here is pi t is current density, and also the gradient of this density. So now with this particular metric, we have this explicit form of this Wasserstein gradient flow, which is given by the pi t of so essentially on the left is still the time dependent, time derivative. On the right, so if you calculate this variation, you end up with this gradient of the log of the posterior distribution minus the gradient of the log of pi t, the current density. And by Leibler equation, we know that this gradient flow is corresponding to a certain dynamics. This is a density involution corresponding to the particle involution of a gradient of a pi theta t. This is given by the gradient of the log of a posterior minus gradient of a log of a pi t, right? We know of the log of the posterior distribution, but however, we do not know the current density pi t. What are we going to do about it, right? So here we can actually approximate it by our current particles, because we have our particles. We can estimate particle density by using kernel density estimate, one of the density estimate, kernel density estimate. It's the sum of all these kernels evaluated the current particles. But however, as you know, for kernel density estimate, the errors are bounded by a certain a convergence rate, which actually scales exponentially bad in the parameter dimension d. And this becomes rather crude approximation here. So essentially, we apply the similar idea. We can project it down to low dimensions. We can also properly rescale and also put a certain metric of this kernel, and then we can end up with this coefficient update. To update the coefficient of this projected prior and posterior, and also the current density in low dimensional subspace. And then our density estimate, we still use the kernel density estimate, but it's much lower dimensional, and also it has a proper metric, either given by let's say the hedging metrics, or given by the sort of like the gradient information metrics. And we show that if the posterior distribution or the log likelihood function, it is strongly convex, and then so the pi t will converge to the posterior distribution in the original space as exponentially, but here we have a convergence rate of lambda d. Lambda d is the smallest eigenvalue of the Hessian of this log of their likelihood function. And typically in high dimensions, it's lambda d essentially is close to 0, or eventually in infinite dimensions, so converge to 0. So this will significantly, slow down their convergence. And in our projected dimension, we have lambda r, right? Lambda r is a properly chosen parameter, and it's evidently different from 0. So essentially, this flow of pt will converge to py exponentially with the exponential rate of lambda r. So this is sort of like the power of projection down to their low dimensions. First of all, it alleviated the curse of dimensionality, and secondly, the particles will converge exponentially faster to their posterior distribution with the red much larger than the original space. Okay, here's a very simple demonstration of this linear inverse problem. We have a theta at Gaussian distribution with this here specific, here's Laplacian, specific definition of the covariance in one dimension. And we have 15 pointwise observations. We have 1% of observation noise. We use 16 samples. And here's a comparison. Because for this linear problem, we know about our posterior distribution explicitly. So can test our error for their mean and also sample variance. And we have the SVGD, PSVGD, and Wasserstein gradient descent and projected Wasserstein gradient descent in dimension of 257. As you can see here, in high dimensions, so our projected version converges relatively fast compared to their low dimensions. And this is the number of iterations for their, for the algorithm. And on the right, you can see more evidently that PWGD is sort of like a converge much faster than the SVGD, and it achieves also smaller error measured by the root mean square error. Okay, so here's a simple test by a nonlinear case. We have a log normal diffusion problem, and this is again is a Gaussian. We have 49 pointwise observations, 5% of observation noise, and now we use 32 samples. You can see as we enlarge the dimension, the discretization dimension, right? Both the SVGD and WGD, they fail to sort of like converge to the right place. And essentially, the root mean square error of the mean of the particles, becomes much worse compared to small dimensions. But in high dimensions, we can sort of like preserve the accuracy of sample approximations. And then for the PWGD, we have a similar convergence of the eigenvalues and also step norms, and also the parallel scalability here. For the last couple of minutes, I want to talk a little bit more about this Wasserstein gradient descent. So Wasserstein gradient descent, we have the update of the particles. I have the gradient of the log of a posterior, right, and minus the gradient of the log of a pi L. And in the last Wasserstein gradient descent, we have the kernel density estimate of this pi L. But now we use different approximations. So essentially, we want to approximate this pi of posterior minus of pi L here, and the log of their terms by a neural network of phi. And in fact, we want to solve the optimization problem of this approximation by taking the gradient of this phi and minus this gradient of all these terms, because once we take the gradient, the normalization constant of the model evidences get canceled out. So we integrate this difference, this approximation difference, with respect to the current density of pi of L. So now we use a two-layer neural network. There is a specific property of the two-layer neural network approximation, and also we use a nonlinear activation function, which is a square root of ReLU function. The reason to choose a square root of ReLU function is because we need to take the gradient here, and also after proper integration by parts, we also need to take the Hessian of this neural network. So then the function space now becomes the continuous function space is represented by two-layer neural network. And then we can directly train this two-layer neural network step by step, right, for each of the given pi of L. And another way, alternatively, we can actually, for this two-layer neural network, formulate sort of like a relaxed dual problem for this optimization problem with proper regularization of the neural network weights. So essentially here we have the weights W. If you put a proper regularization term, so essentially it's quite specific. It's to the cube of the regularization. And this actually leads to a lower bound of the optimal approximation in terms of, this lower bound. So instead of the training of the neural network, we can solve a convex optimization problem by this relaxed dual problem. So essentially, it's a semi-definite programming problem, a convex problem. So we don't have to train the neural network. We just need to, solve a convex optimization for this relaxed dual problem. And again, this convex problem is actually scaled pretty bad with respect to the parameter dimension of d of to the square, and of also the number of training samples n is maximum number of these two terms times another random sketch number, and also to the power 6. So this computational complexity is quite bad for the convex optimization. Now with the dimension reduction, we can go from d squared to the r squared and much smaller. And this convex optimization problem becomes much more feasible. So here's a simple test of the toy problem in 2 dimensions. Again, this is double banana problems with our convex optimization of this neural network. For each of the Wasserstein gradient direction, this is sort of like a comparison of their converged samples with SVN, Stein variational Newton, as a reference. So you can see here the MMD, the maximum mean discrepancy of these 2 different algorithms compared to our reference of SVN samples. And I can see the smaller error by the convex optimization than the direct training of the neural network. And here is a test again by this nonlinear problem. We can see, so essentially this convex optimization obtained the smaller error and sort of like a converged a bit faster. And also by a dimension reduction, we can solve the convex optimization problems for each of the step from like 800 seconds to less than 1 second by a dimension reduction from 81 to 20. Okay, all right. So this is sort of like I've talked about the Stein version of gradient descent and also Wasserstein gradient descent. I didn't mention the Langevin MC specifically, but essentially here is a sort of like a unified understanding. And so originally we have our perturbation map, right? It's a phi of hat. And in the Langevin MC, you simply have the gradient of the log of the posterior minus a certain random walk, and of course you can build the information like a preconditioner. You can build some like other posterior related sort of like a covariance matrix in here in order to accelerate it. And here we have the Wasserstein gradient descent. We approximated our this phi L as our gradient of the log of our current density as either kernel density estimate or a neural network approximation. And in our Stein version of gradient descent is averaged gradient of the log of posterior and also the kernel. So essentially, these algorithms in continuous time, they're corresponding to certain dynamics. So here, the Langevin MC is corresponding to the overdamped Langevin dynamics. It's given as in here. It's dynamics of the parameter, and here we have the sort of like a Brownian motion, and we have here in the mean field Wasserstein dynamics, and it's just simply given as in this gradient of the log of current density pi t, and it's interestingly for the Stein version of gradient descent, it's also corresponding to a mean field Stein dynamics, and this is given by the phi of t. In fact, the phi of t is actually the projection of this term in the reproducible kernel Hilbert space given by the integral here. And by, in this deterministic case, by Leibler equation, we end up at the Wasserstein gradient descent, gradient flow. And for the Stein version of gradient descent, we have the Stein gradient flow. And in fact, this is an approximate of the Wasserstein gradient flow in reproducible kernel Hilbert space. And because of this approximation, typically we observe Weierstein gradient flow converge faster than Stein gradient flow. And on the left-hand side, you can see the overdamped Langevin dynamics by the Fokker-Planck equation in their stochastic dynamics, right? It also converge to the same Weierstein gradient flow. And the Weierstein gradient flow is given, as we introduced a bit early on, this is same gradient flow with this Weierstein metric. So it's sort of like a unified understanding of all these different dynamics. All right, that's pretty much what I want to talk about. And essentially, the TAG-aware message is, by the projection, by the dimension reduction, by the proper curvature information that is built in the variational inference, you can effectively break or alleviate the cursor dimensionality. And also, we demonstrated the scalability of this algorithm with respect to the number of parameters, with the number of samples, and also with respect to their computing power, number of CPU cores. Thank you very much for your attention. I'd like to take any questions. Hi, Rabia. That's a very good question. So essentially, we project down to a subspace, and also we involve this dynamics like quite a few steps until a certain convergence. Let's say like the step size in the low dimensional subspace becomes very small, and then we go back to the original dimension. That's correct, exactly. Yeah, we use the line search. Yeah, that's right. So we sort of like in each of the subspace, we have a measure of our sort of like a posterior information by evaluate properly of a criterion that sort of like prevent overshooting to completely wrong direction. And also we start, let's say, from relatively small learning rate or the alpha L, and we monitor this convergence. And also we sort of like each of the subspace during their evolution of this SVGD monitor this information. And also at the same time, globally speaking, because we constructed these subspaces adaptively, once these parameters or these particles involved well in one of the subspace, and it actually moved to a certain direction, a certain location, right? And then we can recompute our subspace. And so gradually, they will converge to the posterior distribution. This subspace does not change anymore, and you can involve, this information towards the convergence. In fact, we did this projected Stein variation Newton first. We were working on the Stein variation of Newton, and then there come out of your paper. So. Well, because some of the situations you cannot afford to compute the Hessian all the time, right? So, but you can get access to the gradient information. Does that answer your question? No. So we. So in this case, we only use the gradient information. It's not a Hessian here. Well, so you have the Hessian in here, right? Yeah, well, if you talk about it, Gauss-Newton Hessian, it's different. And so Gauss-Newton Hessian and also their gradient, they're different. So Gauss-Newton Hessian, so here you have the gradient of the potential. Gauss-Newton Hessian, you have the Jacobian of the from observable to from parameter to observable map. And in, for instance, like in PDE constrained case, for the Gauss-Newton approximation, you still need to solve the additional linearized problem in order to get the Gauss-Newton approximation for the Jacobian. Yeah, thank you. Yeah, this is also a good idea. So essentially, you can directly approximate this score function instead of approximate your, let's say here, here the log of the posterior. So well, we did a bit of test of that, and we found that comparatively speaking, at least in this two-layer neural network setting, we didn't get as good results as we simply approximated this log of the pi, but certainly there are other algorithms like score-based approximations, but not in this setting.